Hello and welcome to Risk Awareness Week 2020 and my presentation, Production Recovery Planning in the Time of Disruptive Pandemic, using Bayesian thinking to augment scenario analysis. Hello, my name is Robert Brown and I'm a Senior Strategy Analyst with the Global Automotive Group at Novellus Incorporated. So before I go much further, I'd like to give you just a very brief background. For the last 20 years, I've worked primarily in systems engineering and strategic decision and risk analysis as a consultant. Most of my clients have been Fortune 100 level size companies across a wide array of industry verticals, as well as a very broad set of project types. I'm also the author of the book Business Case Analysis with R, Simulation Tutorials to Support Complex Business Decisions. It was published in 2018. And I'm also a 1992 graduate, School of Mechanical Engineering from Georgia Tech. So what I wanted to do in our discussion today is describe to you a method or an approach that I used or am using still here at Novellus to help us modify or update our production schedule on the basis of the shutdown that we experienced earlier this year due to the effects of COVID-19. So let me sort of describe the environment in which we work first. First of all, Novellus is one of the largest flat-rolled product suppliers of aluminum to the automotive body sheet industry. Most of our clients are very stable in terms of their demand profile. They have a predefined production schedule, and we actually match our production schedule to that on the basis of a sort of a periodic roundup that we receive from a few different third-party services that tell us what the next few months production will look like over the next coming year or so. And these forecasts are actually pretty accurate. Of course, we do have a couple of surprises every now and then, but for the most part, we have a stable demand on our products, and we have a pretty regularly planned production schedule that meets that. Unfortunately, we all know what happened earlier this year. COVID-19 caused a massive disruption, catastrophic disruption to the entire economy almost. And for the automotive industry, this meant a very rapid decline and complete into production by the end of March for the next few weeks at least. But we didn't know, of course, at the end of March when we would get started back up again, if ever, really. And of course, one of the problems that we faced is that it's not very easy for us to shut down our manufacturing process because we have smelters that have to sort of maintain a continuously operating state, more or less. And we can't just simply turn the system on and off on demand. So a key question for us would be, when would our customer base restart, or even would they restart at all? And then how should we adjust our own production planning to match their needs, particularly when we're facing a huge amount of existential risk and uncertainty about the future? Well, fortunately, we weren't completely without help in thinking through this. We actually had a few consulting groups that were able to supply us with some well thought out recovery scenarios that may occur. In fact, they provided us essentially three possible scenarios that could describe how the world would evolve as we began to emerge from the shutdowns that had occurred. Unfortunately, none of these resources really provided us, though, with some essential ingredients. And number one was they didn't give us any sort of idea what sort of probability any one of these scenarios could be the case. And they did not supply us with any sort of prediction intervals around these scenarios, so that even if a particular scenario were to evolve, we didn't know what sort of variance would exist around the center line of that particular scenario. So I thought this was a fantastic opportunity then for us to apply something called Bayesian reasoning to our production planning process. And that would help us to decide which scenario could potentially be unfolding on the basis of information that we received when the automobile industry actually began to turn back on and start attempting to produce cars again. So before I go into explaining how that works, what I want to do, first of all, is just very briefly give you a little review about what goes into sort of a Bayesian analysis or Bayesian reasoning process. So first of all, let's consider what we think of or call the likelihood function, and the idea of what a hypothesis is associated with a likelihood function and the evidence that we would get for that. So typically when we are trying to understand the world around us, we might conceive that there are several different ways to think about how the world is behaving, or what is causing the world to behave a certain way. And so we might formulate some hypotheses about what those various causal descriptions are, or mechanisms are. And we might then also come up with a way to measure something associated with those hypotheses, some attribute. And given the way that that attribute occurs, within a given hypothesis, there should be a certain probability associated with that measurement if that particular hypothesis is the case. So for example, let's say, as we'll see in the next slides forward, let's say we measure the height of a person randomly drawn from a population. And based on the height of that person, maybe that person could be considered or classified either as male or female. But of course, there's going to be overlap between those two subpopulations in terms of the heights that they could represent. And therefore, there's a probability associated with each measured height, given that any one of the subpopulations could be the case associated with the sample that you've chosen out of the population. So that describes the likelihood function. It tells us how a particular attribute varies according to a probabilistic distribution, given that any one of the hypotheses about the future is the case, or not even the future so much, about just the state of nature as it is. There's another piece to Bayes' thinking, and that is the prior probability. So we may also have some additional information that would tell us how likely or the proportionality of the subpopulations are, or the hypotheses are. Maybe we have some prior understanding about things that isn't necessarily easy to measure directly, that would give us a belief that one hypothesis is more likely than the other. So we would weight our evidential measurement of probability with this prior probability, and then renormalize the actual result from that based on the total probability of all the hypotheses at that measured state, or that measured attribute. That gives us something that we now call the updated belief, or the posterior probability, on the basis of a measurement. So I proposed that we treat the scenarios as if they were hypotheses in a standard Bayesian reasoning environment. And so I'm going to explain how we do that. But before I do that, I'm going to go into a little bit more detail about how that measurement process works that I just described, related to selecting an individual out of a population and then trying to infer which subpopulation they may belong to on the basis of that measured attribute. So again, let's say you have randomly selected an adult human out of a population of humans, and you measure their height. So their height is the attribute that you're associating with the hypothesis that either males or females can describe the person that I've selected out of the population, right? Now, of course, there may be, and there is, in fact, a variance in the distributions associated with the heights of both males and females. Males tend to be slightly taller than females among humans. So if I were to select a human out of a population randomly, measure their height, and then compare their height to that probability distribution of the heights associated with each of their subpopulations, I can then find out the probability associated with that height within the subpopulation, given that they are either male or female. Now, if the two subpopulations are, more or less evenly proportional to each other, then I really don't have to do much more than that. Any sort of prior belief that I have would be that the populations are evenly, approximately equal. So that prior probability that I mentioned earlier, as you can see, it's easy to cancel out of the formula. And really all I have to do is just sort of find that find the likelihood probability associated with the height. So at 5 3/4 feet, say, what the likelihood function or the probability distribution of the heights of adult humans is how that's, according to how that's distributed, would tell me that there's a 41% chance that the person I've selected is actually a female, and a 59% chance that the person that I've selected is male. But things are a little different when we have some prior belief that the proportionality of the population distributions is different. In other words, maybe we are selecting from a population of humans where we know or have a very strong belief that the proportion of females to males is, let's say, 3 to 1, highly skewed. So again, if we take a measurement of a person that we randomly select from this population, and then scale the height of the likelihood function by the prior probability, and then calculate the renormalized weight of that probability according to the total probability of the two individuals selected at that particular height, it would readjust our belief that the person that we've selected is actually a female versus a male. Now, what I am not saying is that the heights of the females have changed. What I'm saying is that by skewing the proportionality of the populations, it is more likely the case, regardless of the height of the person, until we reach out into some extreme levels of the distribution, it is more likely the case that I'm going to select a female anyway, right? Not a male. So even if I select a person who is 5.75 feet tall, I am 3 to 1 times more likely to select a female, and then that inclination of selection would help me to readjust the probability. And so now I would re-update my belief that a person who is 5.75 feet tall that I've selected out of the population is actually a female. So this is going to be the approach that I'm going to use. There is going to be, however, a twist. And part of that twist is that I'm not going to, let's say, select a scenario that has the highest probability. What I intend to do is actually to combine the possible scenarios according to the frequency of the probabilities indicated. So before I get to that piece, though, let me explain how this process works. So the very first thing that we would need to do, as I just pointed out, is to identify what our initial prior probability is. And then we're going to go through this cycle that I just described on the prior page of measuring the probability associated with each measurement. I'm going to go through that cycle every period forward, about every month forward, when we get new production data in. So on our first month after production has started, we would get a production level. That production level would then be compared to the scenarios that we have, and given that production level, we would generate a probability that the measured production falls within the range that's possible around the center line of those scenarios, and then reweight the probability on the basis of our initial prior probability. Then we take the updated probability and we sample from the scenario distributions according to that frequency that we've assigned to each of the hypotheses or the scenarios. And we produce a sort of a new scenario that represents the convolution or the combination of those samples. And then that becomes the basis for our forecast for the remaining period forward that we have for the fiscal year. We then retain that probability that we calculated, the updated probability based on our measured production, and we set the cycle all over again. Now, notice though that I mentioned that we will have distributions around the scenarios, which I haven't yet discussed how that occurs. So that's going to be the first thing we need to discuss is how do I augment the information that I currently have, which is somewhat sparse. I have essentially 3 potential world lines that could evolve over the next year. And I need to augment that information with the kind of information that I need to perform this sort of Bayesian updating. So the way we do this is, first of all, I am going to increase the number of scenarios that we have. The first thing that I'm going to do is take our, let's call it our original pessimistic case, and I'm going to create a really worst case scenario. That worst case scenario is just a downward revision on the pessimistic third-party scenario, one of the third-party scenarios. And I'm going to create that such that it's more or less evenly divided and gives me a close run to the very bottom, absolute possible worst case of no production. This will allow me to essentially generate, let's say, I'll call it a CYA scenario, right? It's the scenario where we consider that the world, if you'll pardon the expression, goes to hell in a handbasket and pretty much stays there. Then I'm going to take those 4 scenarios and I'm going to average them. And I'm going to create a sort of a midline view of all of the scenarios. So now I have 5 scenarios to use. The next thing I want to do is to put ranges around these scenarios. Now, you'll notice that here I've drawn 3 scenarios, not 5. The reason for this is that I'm going to simplify the amount of information we deal with to have this conversation. So remember, there are 5 scenarios. For the purposes of the remaining discussion, I'm only really going to consider 3 because I'm really focusing more on the process as opposed to the actual specific details. Okay. Another thing that I need to mention before we go further is that you'll notice the numbers that I'm using here. These are fictitious numbers. However, the units are consistent with what we use in our industry. This would be thousands of metric tons, or as we frequently say, kilotons. So the numbers are fictitious, the units are real, and now we can think about how to generate these distributions around the scenarios. So first of all, for the interior portion of the scenarios, I drew more or less probability distributions, if you will, lines, such that they overlap a little bit in the interior portion. They don't completely overlap each other, but they do overlap some. And the reason I do this is because I want to represent that, first of all, I don't know really what the full range would be. So I'm going to start off with almost maximal level of uncertainty, almost, and recognize the fact that as a scenario is evolving, it's not strictly evolving toward just one scenario or another. It's actually probably evolving according to a set of characteristics that combine the elements of scenarios. So there should be possibly some overlap. So if, for example, a production level occurs in one of these interior areas, there's some possibility that it's still being produced by the set of characteristics or attributes that are creating maybe one scenario or the other. And so I need to take that into account. There is some possibility that any one of the two scenarios in this overlapped area could really still be the case. Now, for the outer edges, say the upper edge of the optimistic set of scenarios and the lower edges of the really pessimistic scenarios, I consulted our internal subject matter experts. We had a discussion about the production capabilities, how fast it could take for our OEM customers to ramp up. And we put basically these outer edges on the basis of those subjective considerations. There was no actual hard physical evidence that we had in terms of actual data, but it was based on the on-the-ground understanding of our internal sales and business development people that know how our customers behave and are very familiar with their planned production before COVID, and even what they are capable of doing as they are trying to recover their own systems. Plus, there are just some natural logical constraints on what that could be. And then, of course, on the downside, we more or less limited that in some cases down just to zero itself. However, it was very important that we consulted our subject matter experts on this and got them to explain in their minds why these distributions could exist at all. So then the next step was, once we had sort of drawn these distributions around each scenario, in other words, mathematically what I've done is specified the endpoint parameters. I then use those endpoint parameters, the central tendencies of those distributions, and I'm able to use Monte Carlo simulation to create a simulation with bands of probability around each scenario. So now I have a sort of a variation that exists around each one of the scenarios over time. And it's important to understand that what these will ultimately represent are the likelihood functions that I described earlier. Now, going forward, I'm going to do another little trick. And I'm not going to just use the period-to-period scenario production profiles. I'm going to use the cumulative production scenario profiles. So, in other words, instead of just looking at the production that occurs in a given month and comparing that to the production that's forecasted or implied by a scenario in a given month, I'm going to look at the cumulative production up to that point and compare that to the cumulative forecasted production up to that point. Now, the purpose of this is to actually sort of dampen out, if you will, some of the variation or volatility that can occur particularly during the startup phase, as we go through recovery and as we begin to sort of work out, how to work in an environment where people potentially could continue to spread COVID, where COVID outbreaks could occur all over again and have residual effects on our market. So we know that there is not going to be just a strict conformity to any one scenario in any given period. It will bounce around a bit. So the idea behind the cumulative is to sort of flatten that out and to minimize the amount of volatility. So then, as we begin to move forward in time, when production recovers, we start at least in the first period and we get our first production actual. Of course, we compare that production actual to our cumulative forecasted scenario likelihood functions. And on the basis of it being our first time forward after production begins, I'm going to use a prior probability of 1/5 to represent our initial belief that any one of the scenarios would be the case. Now remember, just because I'm showing 3 scenarios here, I am in fact dealing with 5 scenarios. At the beginning, who knows how the world would have evolved? So therefore, I'm going to use the principle of insufficient reason to say that the only information that I really have are the number of hypotheses to consider, and so I will equally weight them 1/5. But now the next period forward, that probability, that prior probability is going to be changed. But essentially the way I calculate that next prior probability would be to use my initial prior, multiply that, of course, by the likelihood probability that occurs from the measurement within the cumulative production forecast, and then scale that according to the total probability of all of the forecasts in that period of time. So now I get a new set of prior probabilities, and that goes into the cycle again, the next period forward when we get the next month's production, actual production reports. Again, we keep cycling this process every period as we get new information. And hopefully what that should lead to is an improvement in our overall forecasting process about which scenario is the one evolving. Now, there is another piece to this, though. I don't want to just have an idea about which scenario is evolving. I actually want to produce a production forecast. Based on the production scenarios that could evolve, what will the actual production look like from our system by the end of the fiscal year? And then based on that, can we back solve through the remaining months to understand what our production levels should look like each month moving forward? So the way we handle that is that on each period, when we calculate the posterior probabilities, that is the probability using our initial prior probability multiplied by the likelihood probability that comes out from the current measured state of production, and then renormalizing that, I get a set of posterior probabilities. And I use those posterior probabilities to tell me how frequently I should sample from the remaining period-to-period production profile, not the cumulative, but the period-to-period production profile associated with each scenario. So now, let's say scenario 1, it's 50% probability that it comes from that. Let's say it's 30% probability that it would come from scenario 2, and maybe just 20% that comes from scenario 3. Given that, I then sample from each of those probability distributions according to those frequencies specified, or treat those probabilities as frequencies. And then by taking those samples and putting them together into one final set of samples, that becomes my new updated scenario. It's a convolution or a combination of those scenario hypotheses that I have that produces a most likely scenario that's evolving. It's a weighted average, if you will, of all the scenarios moving forward. So what I would want to do then is take the time period moving forward, that remaining time, sum up the result of that sampling of all of my scenarios, and add that sum to the sum of the prior actuals that had been produced. And that will be my total end of the year or end of fiscal year production result. And the effect of that is what we see here. That is, I get a set of risk profiles or cumulative probability distributions associated with each time period moving forward, indicating to me how much production I anticipate to have produced by the end of the year. Initially, in the very first time period, when everything is very uncertain, and I have the possibility of any one of the 5 scenarios evolving, the range of that risk profile will be very wide. But as I move forward in time and gain more information, and as let's say the future begins to collapse into a known determined state, then the range or the precision should improve. And what should happen is that let's say the volatility of my mean value should begin to decrease as well. In other words, the distance between the means that are implied by the updated sampled scenario should get narrower and narrower, closer to closer with every period forward as I gain improved perspective about what the actual production would be over time. And that is exactly what happened. So in production period 1, of course, we had this very wide range. By period 5, we were seeing, a much tighter range. And as we're closing in on, forecast period 9, the range will get even tighter and tighter, and has gotten tighter and tighter, although we're not quite at 9 just yet, but we're getting there. In the meantime, we've also had the opportunity to review these results and ask ourselves, does this still make sense? And that has actually led to a couple of interesting observations. And so one of which I've already mentioned is that although this is a work in progress, I think it is working as it's anticipated. But it has led us also to remain in a very close contact with our subject matter experts, our internal experts, who have given us, let's say, updates to their understanding about what the OEMs are actually doing, on the ground in their own environments. So sort of jumping ahead on the bullet points here, but I think it's very important as you implement a process like this that includes, at least initially, some very subjective understandings about the distributions that can be employed. You stay in close contact with those subject matter experts and adjust the shape of your distributions as you evolve. Incorporate that information in what you know and believe, and build up that sort of book of bets, if you will, around the distribution profiles. I want to say, though, that this situation seems to be best suited for at least situations in which you have a defined upper bound, and is the environment that you're dealing with is usually very stable during equilibrium periods. This problem also is actually very similar to change point detection type problems. So even if you're not concerned so much with how do I update a production profile, but you just simply want to know when is a system equilibrium switching or changing over to a new equilibrium or a new regime, at least that has some sort of near-term stability, you can use this approach to possibly help update those probabilities that any one of those regime periods are the case, or any one of those regimes are the case within a certain time period that you're looking at. So anyway, that's sort of how I'm using Bayesian reasoning in a real-life example to incorporate knowledge that we have from trusted sources, subjective sources, and actual objective sources, right? The actual measured amount of production that's occurring, and helping us to readjust our own cycle or our own production profile planning process on the basis of that kind of information. So it's experimental, but I invite you to consider it for yourself. And if you do decide to try to use it, let me know how it works for you. In the meantime, I hope you all stay safe and can avoid the worst effects of this pandemic as we move forward. And hopefully we will all be back to a recovered state very quickly. Take care and have a good day.